Okay, so we're going to pick up where we left off. So the last thing that we did is that we showed the trivial case, and we did the setup for the case where P0 does not equal P1. And now, we noted that we were going to begin by showing that the statement was true for the simple functions who are non-zero outside, are non-zero in a finite measure set. So, so what we're going to do is we're going to define two of those functions. So first, we've got a characteristic function for ej's living in x and complex coefficients, and some of them equals f. We're also, and then we do the same thing for g, where the characteristics functions for the fk's now live in y. And what we get, and then we insist that they are non-zero, that the coefficients are non-zero, and we insist that they are in fact partitions of their union, so they are no two sets overlap, so they're mutually disjoint. So for all x not equal to y and w not equal to z, y intersect ex is the null set equals fw intersect fu. Okay? Now, because these are complex numbers, we can write them in their exponential forms. So magnitude times direction, magnitude times direction. Then we're going to define these functions alpha and beta, where they're just the inverses of the pt's and the qt's. So we have 1 minus t, p naught inverse, t, p1 inverse. And by inverse, I mean these are numbers, so reciprocal. And then the same thing, 1 minus t, q naught inverse t plus t q inverse. So this is just a simple path from p naught to p1 and from q naught inverse to q1 inverse. Okay? Now, we remember because p is not equal to, p naught is not equal to p1 by assumption, we have that pt is finite, which means that alpha t is greater than 0. And because of that, this function here, f sub z, which is going to be a complex valued function on the strip from 0 to 1, and which is defined using the definition of f, but replacing the power of the magnitude of the coefficient by alpha z divided by alpha t. Because alpha t is non-zero, this is well defined. Now, and then we do the same thing for gz. However, with gz, we do not get the same, we cannot claim that bt is not equal to 1, so, or beta t is not equal to 1. So this is undefined at beta t equals 1. So we write it as a piecewise function where we give the definition of the function to be g when beta equals t, when beta t equals 1. So that's a well-defined function. And we're going to work with this second case separately. So basically, this everything that's going to come next is going to be working with this first instance, and then we'll make a quick side note about why the second one is true as well. So moving over here, is that well? Let's see now. Let me move the light source. How is that? Okay, so what we have now is we're going to define this function phi z, which is going to be a, I'm sorry, I actually made a mistake over here. These are not complex valued functions. These are valued in x, in the measure spaces x and y. We're now going to use them to define a complex valued function phi z. Sorry, I misspoke before. So we're going to define phi z to be the integral of the image of f phi z, the image of fz under t, gz dv, and we can write that using this sum here. And the reason that we can do that is because f and g are defined using disjoint unions or disjoint sets, so characteristic functions of disjoint sets. So since we have two lists of disjoint sets, to find a partition of the union of the two lists of disjoint sets, we take the intersection between every possible pairing from the two sets, which is what the AJKs are, where we take the direction of the complex number, that's the coefficient, on the product of two of the coefficients times the integral of the product of their functions, which is their measure, and which is the measure of the intersection of the two sets, EJ and FK. And we have that, and then we have that the product of the powers are CJ to the alpha z alpha over alpha t, dk to the 1 minus beta z over 1 minus beta t. So these are the magnitudes of the complex coefficients. So we take the product of the powers times the direction times the measure of the set that particular pair product of coefficients represents, and that would give us the integral of our product. So because these are both simple functions. So now what we get is that B is holomorphic function of Z on the strip. And the reason that we have that is because the definition, it is the integral of simple functions with Z in the exponent of the simple functions. So we're taking the integral of a piecewise set of exponential functions, which is holomorphic. And then because we have that it's holomorphic, we can apply the three lines lemma. If we have two conditions hold, we need to show that phi of Z is less than M naught. And when the real part of Z is less than 0, and that phi of Z is less than M1 when the real part of Z is equal to 1. And the reason for that is because when Z is equal to 1, we have, when Z is equal to 1, we have the so it's defined on the strip, because if we have the real part of Z is equal to 1 is bounded by this one, and the real part of the function evaluated at Z when Z's real part is 0 is bounded by M naught, and it's bounded by M1 when the real part of Z is 1, then by the three lines lemma, we get that it's going to be, when Z is in the interior of the strip, it is going to be bounded by the product here. And that's directly from the last theorem that we proved, theorem lemma 6.26, which is the three lines lemma, and that's what we need here. So all we need to do is show that those two bounds hold. So what we're going to do to show that is we're going to use Holder's inequality and the fact that this is in fact the L1 norm. So what we're going to do is we're going to note alpha of IS is equal to P naught inverse 1 IS P inverse 1 minus P0 P naught inverse. And then we get the same thing here. 1 minus beta IS is equal to 1 minus Q inverse naught minus IS Q1 inverse minus Q naught inverse. And then that gives us this identity here. And I have so that's a lot to handle, but I did it on a separate board, so give me a second. I'll pop that up here. But what we're going to get is that because we have that F sub IS is equal to FPT over OT, we're going to be able to use Holder's identity and then cancel something on phi of IS, which is the imaginary part. So we're going to be showing for given vertical lines in the strip that we are bounded when the real part is 1 and when the real part is 0. So real quick, I'll pop this right here. So when I consider alpha of IS, that visible. Yeah, there we go. So this one. Okay, so we have alpha IS is equal to 1 minus IS, and this is just following directly from the definition of alpha here. Right? We have that it's 1 minus IS P naught inverse IS P1 inverse, which we can then simplify to here. And then because we have that the absolute value of Fi is S, or the modulus of FIS is equal to F to the real part of this thing, when we expand it, what's going to happen is we're going to drop off. Where's my mark? We get to drop off the complex term here, and what we're left with is P naught inverse over this. But this thing here is just P of t, is just alpha t, but alpha t was pt inverse. So because we have P naught inverse over pt inverse, that's the same thing as pt over P naught. So that's where over here we get our desired identity here. Okay, then moving this away for a second, then what we get to do, by the same argument, we have that for G as well. So we also get that G sub I, that this guy is going to be G Q prime T over Q prime naught. So we're going to get the same thing. And again, the it's going to be because the complex part here is going to cancel out, and we get to use the same algebra as used before. So of just taking the inverse. So from there, what we get is now we can write this as phi s is less than, so phi s, again, there we go. So phi s was defined as this integral here. Defined as this integral here, but this is just the L1 norm. So we can use Holder's identity. Since Q naught and Q naught inverse are conjugate exponents, we get that this is less than the product here. Then, by hypothesis, we said that the image of a function in the Q naught norm is less than M naught times that function in the P naught norm. And then from here, we use our clever trick that we can replace FIS with, or the modulus of FIS with the modulus of F raised to the PT. So, or sorry, PT over P naught. So because this is raised to the P naught power, the P naughts are going to cancel, and you're just left with raised to the PT power. So we get that the norm is going to be the PT norm, and same thing here, because this guy can be replaced with G to the, what was it? G to the Q prime over T, or Q prime T over Q naught prime. We get that the Q naught primes cancel in the norm, and we're left with Q. Then we have, and again, this is because the interior powers and the exponents are, or inside the integrals, are going to be the reason that we have the inequality. And then we get that by hypothesis, we had chosen both of these to have norm 1. So we get that this is equal to our m naught. So now we have a bound on our function when phi of is, when we take phi of is. But this is when the real part of z is 0. So we met the first criteria for using our 3 lines lemma, which was that when the real part of z is equal to 0, that phi of z is bounded by m naught. Now we need to do the same thing for when it's 1 plus si, because when it's 1 plus si, we have when it's 1 plus si, we get the same thing. So we have alpha of 1 plus si. We're going to get 1 minus 1 times 1 minus 1 minus is p naught inverse plus 1 plus is p1 inverse. And then that's going to the ones are going to cancel. We're left with this guy. And then we use the same algebra that we used before. We have that the modulus of f sub 1 plus is. We take the real part in the exponent in this form, and then we're going to do the same thing. We're going to throw away the complex portion of it, but now, because it leaves us with the P1 inverse here, we're going to get PT over P1. So we get to use the same algebra, and again, it's going to be the same thing for G with Q prime 1. We're going to get to use the same algebra again here. We simply replace. Here we have plus 1 plus is. Here we get f 1 plus is, g 1 plus is. And now, instead of canceling, then again, we use Holder's identity to get here. And then by our hypothesis, we get that we can replace the Q naught norm with the P naught norm and add our coefficient. But now we have 1 plus is and 1 plus is. And then we get to do our trick where we cancel. But now, instead of replacing, but now, because this is replaced with Q1 and Q naught 1, we now get that we can now do the cancellation trick again. So because we use the Q1 norm and the Q prime 1 norms, we get by our hypothesis that this is going to be M1. And then we can, and this is going to be P1. Then we get to use the same cancellation trick because now we have P1 and Q1 prime. So our same algebra is going to work out again. We get that it's less than F of PT, G of PT. But now we have M1 here and M1 here. So now we have that it's also bounded at the other end of the strip. So when C has a real value of 1, we have it bounded by M1, which means that we're allowed to apply the 3 lines lemma, and we have that our inequality, F of T QT, is less than M naught. Oh, sorry. We have our inequality that the QT norm, that F of T in the QT norm is less than M naught to the 1 minus T, M1 to the T times F of P, and we get that using the 3 lines, and that it directly follows from the 3 lines lemma. So now we have proven the case when we have simple functions who are non-zero only on a finite measure subset. And the last video, which is going to be the next one, is going to be completing the proof and extending that to the set of all functions in LPT. Okay, so I'll see you guys in the next video. Bye.